Hello everyone. In last lecture, we started to talk about deep neural networks, and we introduced specifically a neural network with one layer, one hidden layers, for regression with a single output, and a regression with multiple output. And in today's lecture, we're gonna give a little bit more motivations where this idea of neural network comes from. Actually, it's come from the neurobiology. Recall what we have here is we have several input features, right? So suppose we call it x1, x2, xd. Okay, we also include a constant. Usually we include constant bias. We call it bias in neural network. And then we have several hidden layers, which we denote h, h1, h2, hk. Okay, the hidden layers. And then we use this linear combination of this hidden layer. You can think of this hidden layer are just the transformed features of the original ones. And we also want to include the bias term here too. And then we use this to either predict the single label. So in today's lecture, I'm gonna using the demonstration example using the classification. With multiple labels. So multiple labels, so which means you need to produce the probability for the probability of the first class, the probability of the second class, and so on. So we have also the multiple. Okay, we have the label M. So one example, and then we construct the linear transformation, and then we apply some of the activation functions. So for example, you have the weight, right? So we call this weight V, and we call this weight as weight W. So each variable transform, each hidden layer node is a linear transformation of the weight from the first node, from the first one. Okay, weight, the second variable to the node 1 until the weight. First hidden layer from the this input node. Okay, and then we have the bias term too. So 1, 0. And then you do the same thing to each of the hidden layer node. And then we get a new transformed random transformed features h1 and hk, and then we also apply similar techniques to get the. So here we introduce the probability, introducing the classification. So we need to, the output of this neural network will be, you can think it's the transformation of this into, we need the output to be the probabilities, So here you can think of the motivation example is the, I can give you this MNIST example. Okay, so in the MNIST example, we are trained based on the people's handwritten letters. So each of the handwritten letters, we learn this from our lab or homework. Actually, each number, each handwritten picture can be decomposed into the 28 multiplied 28 pixels, and which is so it's 28 by 28 pixels, which has each of the pixels has a value from 0 to 255. So in other words, each input x is you have the first value, you have the x1 up to x 28, 20 times 28. Okay, so this is the input. So this dimension d here equals to 28 times 28. So this is our input dimension here. And the number of hidden layers you can decide. And the output will be the, here we want to predict the probability from 0 to 9, right? So you need the output in this case will be, so each z1 represents a probability to get the first label. Maybe 0, right? And until this is a this m, so in this case m equals to 10. And we constructed this neural network with one hidden layers. With hidden layers, we can get the so this is our model. Label for the w label for the w is same. Second weight is same. Oh, I think this is v. This is v. So up to the first label, from the first hidden layer. So this from the to the first output label from the second layer and so on. So here we have k of them. So these are the w weights. This is the w weights. And recall that our neural network transformation formula is the V matrix times the input x. This including this one Bayes. So last component is our Bayes term. Okay, and then we transformed by some activation function. Usually it's so this is h vector. So h vector. Okay, so this v. So this matrix V, recall how many hidden layers. So it's k multiply how many input features plus 1. So it's d plus 1. Okay, and this x has dimension d plus 1, right? We have the d input with one Bayes term. And then we apply this activation function, either sigmoid or the ReLU activation function. We get the first hidden layer. So first hidden layer we will have the dimension k. And then once you get this h hidden layer values, and then you apply to this w matrix. So it's w multiply this h. Okay, so w will be a matrix with how many output. So it's m output multiply how many inputs. Input is k plus 1. Okay, so this is dimension of the w, and the h has dimension k, but we want to augment it 1, so it's k plus 1. So the output will be, and then we need to apply some if it's regression, we just use this function as our output. If it's for classification, like the example here, we need to construct some final output function. So it's z will equals to s. So this is S1. Remember, S1 is you apply the S to each of the nonlinear node and leave the 1 at the last component. Okay, so this is our neural network function. Actually, before we go into details, I want to give you a little bit of introduction. Where is this neural network idea come from? Actually, it comes from the neurobiology. Maybe let me give you some pictures of the neurons. Actually, the field of the artificial intelligence, they started maybe a little bit of history about artificial intelligence. So the early AI researchers attacked the problems like chess, beating people on the chess, and theorem proving, because they saw this gonna exemplifies the essence of the intelligence. But they didn't pay much attention to at first to the problem like a vision or the speech recognition understanding. So which any 4 years old boy or kids can do these things, and the researchers underestimate their difficulty. Today, we know what this machine learning, deep learning can do better. Computers can effortlessly beat 4 years old at chess, but they still cannot play with toys well. We have come to realize that the rule-based symbol manipulation is not the primary defining the mark of the intelligence. And the neural networks are partially inspired by the working of the actual brains. Okay. So we try to mimic the neural network by mimicking the human brains. Okay. So let's take a few look at about what's the similarity between the neural network and the brains. Actually, for any modern computers, the CPU are largely sequential, and it can calculate the nanosecond gates. But on the other hand, our brains are very parallel. Each neuron fires the spikes. Could be in milliseconds, which is relatively slow, but it can do some of the job much faster. For example, but anyway, so the deep learning network can be think of as each layer is a neurons, each neurons. So neuron, okay, it's just a cell in brain. Or you think it's the brain or nervous system for thinking and communication. Action potential or spike, you can think it's so these neurons, these fires. You can think it's an electrochemical impulse fired by the neuron to communicate with other neurons. Okay. And axons. You can think axons are the limbs along which the action potential propagates, and then it connects to the output. Our brain direct. We need to move our arms or walk, right? And there is also some important connections between neurons it's called a synapse. Synapses are connections from one neuron's axons to another neuron's dendrite. So dendrite is a smaller lamp by which neuron receives the info. So the upper neuron shoots the signals from the axons, and it can get connected by this synapse, and received by another neurons by this dendrites. Also think the synapse are the axons terminals, and the receivers of the next neurons is called dendrites. Okay, actually there are so we have the neurons, axons. You can think axons are the weights in the deep learning, and we have the connections between the different neurons by the synapse. Okay, we also have the receivers from the next neurons. It's called dendrites. Okay, and there are actually analogies between brains and neural networks. Okay, first, the output of unit. You can think output unit either from the input to the hidden layer or from hidden layer to the next level of the output. So you can think this is the firing rate of the neurons. Okay, action potential is have the actually the output of a neuron is not signified by the voltage like output of the transistor. The output of the neuron is the frequency at which it fires the signals spikes, and some of the neurons can fire nearly like 1,000 times a second, which you might think of as a strong output. Conversely, some types of neurons can go for minutes without firing, but some types of neurons never stop firing. For those, you might interpret a firing rate of 10 times per second as a zero. It's shooting zero signals. And so we have the output. You can think output is the shooting, sending the spikes from the neurons. Okay. Also the weight between the layers of the neural network. Weight of the connection, you can think it's the synapse strength. Okay, so positive weight, you can think it's excitatory neurotransmitter. Okay, negative weight, you can think it's inhibited neurotransmitter. And the linear combos of the input. Linear combination of the input. You can think here is when we construct, we have the linear combination of the input, right? So each linear combination input is corresponding to like a summation in your brains. A neural fires when the sum of its input from the several neurons integrated over time reaches a enough voltage. However, the neural body voltage also decays slowly with time. So if an action potential are coming in slow enough, the neural may not fire at all. And then we also have the activation function, right? The logistic or sigmoid function. Or we have the ReLU function. You can think of this as a firing rate situation. A neuron cannot fire more than 1,000 times a second, nor less than 0 times per second. This limits its ability to overpower the downstream neurons. We accomplish this same thing with the sigmoid function. And so we also have we train our model by tuning those weight changes, right? Or learning. We use the batch gradient descent algorithm with backpropagation skills. This corresponding to the synaptic plasticity. In the neural networks. When we construct the original idea of this deep neural networks, actually people trying to mimic how brains functions, but the brain is very modular, and each part of our brain can think is a combination of the several functions. Like one part of the brain controls the language, one part of the brain controls the abstract thinking. It's very subtle. So I think there are a lot of the more details about brains that deep neural network can learn from. I think in this video I just give you some motivation of the deep neural network, and in next video let's talk about the neural network for the classification.